Do you all see that?
So would it be negative sine squared?
You could put negative sine squared at this point, yes. Y'all got this? I know it's messy, but that is true, right? All right, check what happens here. What happens now if you let x go to 0? What do you get on top? Sine of 0? Sine of 0, 0, 0. So 0 on top, and then unfortunately, 0 times 1. 0 over 0 still, right? So we're going to have to use L'Hopital again. Yeah. Nobody said this was going to be simple.
So when they get this long, is there a way to just do the limit definition?
Well, this is, we're not doing derivatives. Wait, I'm not sure I understand your question.
I guess I asked it weird. So like there was a way we were finding limits before L'Hopital's, right?
Yeah.
When they get this long, is it better to just do the first way?
There's no way to do it the first way with this. Like, I mean, on this one, on this particular one, maybe, but generally speaking, L'Hopital is going to help us most of the time. So, all right, I'm gonna rewrite this. Again, notice I'm bringing that natural log with me. I went ahead and made that a negative sine squared on top. Now I'm going to do L'Hopital, right? I got to do derivative on top and bottom now. We're getting close, okay? We're almost here. L'Hopital, limit, x goes to 0 from the right. Okay, on the top I use chain rule. Negative 2 sine x times cosine x. All over. Derivative on the bottom is a product rule. So cosine x.
Negative sine x? Yeah. Negative sine x.
Minus sine x times x.
Isn't that just tangent?
No, because there's minus here. This is a minus, not a negative.
But we're adding it, right?
Where?
Cosine?
We're here?
No, in the bottom.
Oh, you mean, okay. Why did I put x? Oh, what did I not put? No, that was right. That was right. Hold on. So we did product rule. It was derivative of this, which is 1, times that. Boom. Minus, or plus, sorry. That was plus, but then derivative of cosine is minus.
Yeah.
And then times that.
Negative sine x. Yeah. Times
Are y'all all on board with that? Everyone got that? You sure?
x.
Just getting like nods of sure. Let x go to 0 now. Things are going to work. Because this up top is going to become 0, isn't it? Sine of 0 is 0, cosine 0 is 1. So the top goes to 0. That's actually bad, but look at what happens on the bottom. Cosine of 0 is 1. And then sine of 0 is 0 times 0. That's 0. So 1 minus 0 is 1. And 0 divided by 1 is 0. Right? That's not our answer. Hold on. That's not our answer. What did we want to know? Go way back. We want to know what y was, right? We want to know what y was. What do we know? We know that natural log of y equals what? 0. Now, how do you get y from natural log? You kill the natural log. How do you kill the natural log? With the e. So what I'm going to do now is I'm going to apply e to both sides of this equation. I get e to the natural log y equals e to the 0. So I'm doing e on both sides. And what does the left side become? Y. And what does the right side become? 1. So your answer is 1. The limit of that is 1. That's a lot. Yes, I agree. All right. I know y'all definitely have that look of like you've been on spring break or something. Please put several stars next to this one. This is a classic problem. Classic meaning The result of this problem is a major result in Cal 1. What is the limit as x goes to infinity of 1 plus 1 over x all raised to the x? So let's first try and figure out what the hell's going on here. Let's let x go to infinity. Talk about what happens. 1 over infinity. Fixed over big number is headed to 0, right? Okay. What's 1 plus a really small number going to be close to? 1 plus a really small number should be really close to 1 still, right? So the base of this is headed to 1, right? Where's the exponent headed? To infinity. This is an indeterminate form. Now why? Because the number 1, right? The number 1 raised to any power should be 1, right? 1 squared, 1 cubed. 1 to any power should be 1, right? But see, this number down here is not 1, is it? It's a little bit bigger than 1. So if you take a number that's a little bit bigger than 1 and start raising it to a huge power, then it wants to get bigger. And so they're, again, at odds with one another. The base is like, hey, I want to be 1. And the exponent's like, no, I want to make you bigger, and you're not 1 to start with. So, like, who wins? Who won the last battle? What was the problem we just had just a second ago? We had limit x goes to 0 from the right. It was x to the sine x, right? That was the problem we had? The base was trying to become 0, and the exponent was trying to become 0. We had 0 to the 0. And I told you that the conflict here was that the base wants to be 0, but the exponent wants to turn it into what? 1. Who won this battle? The sine x won the battle, right? What was our answer? It was 1. So the sine x actually won that fight between the two. Here, the base wants to become 1. The exponent wants to make this thing huge. So who wins this fight, right? We're about to see, all right? So this is an indeterminate form. And so what I'm going to do to start is I'm going to bring in natural log on both sides. I'm going to pass the natural log past the limit and put it right here, like that. And that allows me to pop the x out, doesn't it? I mean, that's the whole point of bringing the natural log in. Pop this x out. X times natural log of 1 plus 1 over x. You can't pop that x out in front unless you have a natural log, right? You're not just allowed to pull powers out. You have to have the log. Let's check to see what happens. As x goes to infinity, this goes where? Infinity. Okay. As x goes to infinity, what's 1 over infinity? 0 plus 1, 1. And what's natural log of 1? We did this in class. Natural log of 1? College algebra? No? Natural log of 1 is 0. If you go to your natural log graph, it hits right there at 1, 0. The natural log of 1 is 0. So what's happening here? You've got infinity times 0, and that's an indeterminate form. One of them's getting big, the other one's getting small. They're being multiplied. Who wins? You don't know, right? I told you, I promised you that all 3 of these, right, would turn into one of these if we did this method. And now we have it, right? So what am I going to do? You get 0 times infinity. What do? Drop 1. Which one do you want to drop? Do you want to drop the x, or do you want to drop all that crap? The x, right? The x. I think it's obvious, the x. So I'm going to continue writing. Natural log of y on the left-hand side equals limit x goes to infinity. I'm leaving the natural log of 1 plus 1 over x on top, and I'm dividing it by 1 over x on the bottom. And now you can check for yourself. We will check If x goes to infinity, 1 over infinity goes to 0. 1 plus 0 is 1. Natural log of 1 is 0. The top goes to 0. And the bottom, 1 over infinity, goes to 0. And so you get 0 over 0, so you can use L'Hopital now. And as bad as that looks, it's actually not that bad. On the top, you have natural log of something, right? How do you take derivative of natural log of something? 1 over that something times the derivative of what's in here. Take your time here. What's the derivative of what's in here? What's the derivative of 1? 0 plus what's the derivative of 1 over x? We've done this a couple of times. Negative 1 over x squared. Right? You sure? Over? Derivative of 1 over x again, right? Negative 1 over x squared. Why is that awesome? They cancel out. Right? Those canceled out. So all we're left with is this. I'm going to leave that up there. I'm going to erase this part right here. We're left with natural log of y equals the limit as x goes to infinity of 1 over 1 plus 1 over x. And if I let x go to infinity here, 1 over infinity goes to what? 0, and you just get 1 over 1, which is 1. So the natural log of y equals 1. That's not our answer. Because remember, we wanted to know what y was, right? So how do we get y back? How do we kill off the natural log? E on both sides. So e to the natural log equals e to the 1, right? And that means that the left side is y and the right side is what?
1.
No, e to the 1. Yeah, but just e, isn't it? E,
Because y, yeah, because e.
right? E to the 1 is e.
And then times 1.
So here's what we're actually saying. Here's what we're actually saying. We're saying that the number e, you know, you've learned that number e? You said about 2.718? E, by definition, is the limit as x goes to infinity of 1 plus 1 over x to the x. Right? That limit is equal to e. You can define e this way. Now, to understand what's happening here is, I mean, and I'm not going to ask you to do this, but if you want to, you can. What we're saying is that if you take this expression, 1 plus 1 over x raised to the x, if you take that expression and start plugging numbers into this and let those numbers get bigger and bigger and bigger, you're going to get closer and closer to the number e. If you don't believe it, try x equals 1,000. If you go to your calculator and do 1 plus 1 over 1,000 and raise that to the 1,000th power on your calculator, you're probably going to get a number close to 2.718. And if you're not happy with that, you could go even bigger and plug in like 1,000,000. If you do 1 over 1,000,000 plus 1 and then raise it to the millionth power, it's even closer to 2.718. And the further you go, the closer and closer you get to the true number e. If you could go forever, if you could actually let x get infinitely large, then this thing converges to e. Graphically, if I go to Desmos and I graph that as a function, y equals 1 plus 1 over x, and then raise that to the x, do you see that I have a horizontal asymptote? As I move out to the right, do you see I'm kind of like flattening out? Well, guess what I'm flattening out to? Y equals e. I'll put that as a dotted line. So if I graph y equals e and zoom in here, let me use my mouse. You can see here that in the beginning, right, it gets closer and closer, and the further out I go, right, the further out I go, the closer I get. If I zoom in, I'm not quite there. I'm not quite at e, right? But I can go further out Let me see how far I can go. Go out to, let me go out to like 5,000. I go out to 5,000, zoom in. They're almost indistinguishable. There we go. So if I get on the green one, you can see it's rounding. Do you see it's rounding? 2.718, right? But really, do you see these decimal points? To get more decimals out of E, to get more decimals, you just go further out into this. This is the way your calculator knows, 2.718. The way it calculates that is it just plugs in big powers of X into this, and it gives you that as an approximation of what E is. So this is a classic example because at the end you have a definition for E, right? All right. There's one more thing I want to say on this. Who won the battle? Do y'all remember what was the base going to? The base wanted to become what? 1, and the exponent wanted to become infinite. So it was like the base wanted to be 1, the exponent wanted to turn into a bigger number, and who won?
The bigger number. The infinity.
They shook hands. They said, we're going to E, right? It was a compromise. No, I mean, seriously, it's a weird thing. Like, neither one of them won, right? It was this weird kind of in the middle. So your answer is never going to be one or the other extreme. It could be in the middle.
I would say that they get to compromise a lot more.
Yeah, you think? Yeah, you could argue that. So E is obviously an important number. We talked about how important E is, right? All right, I'm going to give you one more example, and then I'm going to give you a few to work on. And to make it worth your while, we'll do it as a grade. All right?
A group quiz?
Like a group quiz. Yep. All right. So this last one I'm going to do, I've done one like this, right? I've done one like this. Let's just do one like this now. All right? Let me see if this worksheet had one. We're trying to do infinity. Oh, okay, that's a cool looking one. All right. Limit x goes to infinity of natural log x raised to the 1 over x. X is going to infinity. All right, where's the base headed? What does the natural log function do as you head to infinity? Infinity, right? We've graphed the natural log several times. Here's the natural log function, right? As you go to infinity, this way, the graph grows, right? It grows. It's not very fast growth, but it does grow, right? Okay, so the base is headed to infinity. Where's the exponent headed? 1 over infinity. What's 1 over infinity? Or a fixed number over huge? 0. So we have infinity to the 0. Why is that an indeterminate form? The base is like, I want to be big, right? I want to be big. And the exponent's like, well, hold on, man. Hold on. What do I do to things? Raising to the 0 does what? Turns into 1. So it's like, slow down. You're not going to become infinite because I'm going to try and turn you into a 1. So again, they're in conflict with one another. So we do natural log on both sides. Bring the natural log inside the limit. We'll have a natural log of a natural log, right? Kind of weird. It's natural log of natural log. Pop the 1 over x out. Natural log of x. That's a double natural log there. Now look, if you start with one of these three, if you start with one of them and you do this method and you pop this out, I promise you that's going to look like that 0 times infinity. You don't need to check it. It should be, all right? But we could check. If x goes to infinity, 1 over infinity goes to 0. Natural log of infinity is infinity, and then natural log of infinity is infinity. So this is infinity, this is 0. You have that same issue. Drop 1 down. Now which one do you want to drop? 1 over x. In fact, what happens when you drop 1 over x down? It just becomes x, right? Like, because it's 1 over x. Or you could just say this x was already on the bottom, wasn't it? However you want to look at it, it doesn't matter. You get limit x goes to infinity, natural log of x over just x. And now you have infinity over infinity, and you can use L'Hopital. This one's actually working out pretty nice. L'Hopital, limit x goes to infinity. Okay, be careful on the top. Derivative. What's the derivative of natural log of something? 1 over that something times, now the derivative of what was in it. What's the derivative of what's in it? 1 over x, right? Because it's natural log. So 1 over x again, or not again, but 1 over x. Done on top, right? Derivative of the bottom? 1. Let x go to infinity. I think things are going to be nice here. What's natural log of infinity? Infinity. So this is 1 over infinity. Where does 1 over infinity go? 0. Okay, 1 over infinity again, 0. 0 times 0. On top, you get 0 over 1. This is just 0. And so we're not done. Natural log of y equals 0. Now you have to get y, so you kill off the natural log with e. E to the natural log y equals e to the 0. And that means that y equals e to the 0 is 1. So who won this one? This one wanted to get real big. This one wanted to turn it into a 1. The exponent 1 in this case. Will it always win? No. It depends on the function. All right, let's do a quiz. I'm going to give you 2 problems, and you're going to have the rest of class, which is what, 20 minutes. Both problems are going to be like these, and that way that forces you to do this. Okay? You can work together. You can use your notes. Okay. Yeah. Let's just get right to it because I want to give you time. Everybody's turning in their own paper. Y'all hear me? Everyone's turning in their own paper. Don't do it on the back of your notes. Do a fresh sheet of paper. All right. First one's going to be pretty straightforward. Yeah, here's the first one. Do the limit as x approaches 0 from the right of x to the x. That's like when you're first learning it, that's a pretty basic one. Limit x goes to infinity of x to the 1 over root x. So be careful because one of those is approaching 0 from the right, and that one is approaching infinity. So they're slightly different. All right, good luck. Have at it. Enjoy.